Welcome to Chapter 8. One of the things you learned about when you were in your intermediate algebra classes was complex numbers. We definitely made that definition and had you work with them. And there are trigonometric forms of complex numbers that really help us work with them in a good and efficient manner. And so some definitions that we want to remind you of. The imaginary unit I is equal to the square root of -1. And so because I is equal to root -1, therefore I squared is -1. A complex number has the form of a plus bi. So a complex number could look like this, 3 plus 2i. Right here, the a that they're referring to is 3, the b that they're referring to is 2. It could also be 3, right? Here a is 3 and b is 0. It could be 2i. Here a is 0, b is 2. Right? All of those. So the complex numbers contain all the real numbers as well. And so it's a larger number-based system. Not base system, but it's a larger number system, right? Just like we've been working with, we started out with counting numbers and made whole numbers, then made integers, then made rationals, then made reals, and now we're building ourselves up to the complex number system. And so complex numbers are really nice because they add algebraically. You add their real components together, right? That's what this is saying. Let me highlight what I'm talking about when I say this. That's what this right here is saying, that you just add the reals and the imaginary, you subtract the reals and the imaginary. And here you would just do FOIL, right? You may look at that and think, oh, that's hard. All that's happening there is FOIL. Nothing to memorize, right? And notice that if we FOILed this one out, what we call the conjugate, we would get a plus b squared because of the I squared being -1. So let's talk about the fact that I squared could be -1, or is -1, not could be. That leads to what we call a cycle of I, which books will take advantage of, and I'm sure you saw in your intermediate algebra class. I haven't taught intermediate algebra and not had it addressed. So we know we have I, and the I squared is -1. So when we go to find I cubed, remember what I cubed is. It's I squared times I, which is -1 times I, and so that's -I. And so what's I to the fourth? I to the fourth is -I. Well, let me write it like this. Let me take a step back. Okay, it is I cubed times I. Well, what's I cubed? Well, we just found out I cubed was -I times I, which is -I squared. But remember what I squared is. I squared is -1. What's the negative of -1? 1. So that means that if we keep going, I to the fifth is going to be 1 times I, or just I, and we're right back to here. So I to the first is the same as I to the fifth. And so I to the sixth would be the same as I squared, which is -1. Now notice something. It's repeating itself after 4 iterations. Take a look at something. If you were asked to do I to the sixth, an easy way to know that that is -1, or I squared, is to take 4 and divide it into 6. Recognize that it goes in one time, and it's this remainder that we pay attention to. So I to the 6 is going to be equal to I to the second, which is -1. And that's the cycle of I. We'll see if they have problems like that, but theoretically we could do anything now. You should never have an answer that's written as I to a power. Everything should just be in terms of I. So if I go in here, lots of little marks here to get rid of, but I just needed some space. Here's what we should be able to do, because we understand the cycle of I, that it repeats every 4 times. If I do something like I to the 127, no problem. I would just have to figure out how many times 4 goes into 127. Actually, don't care about that. One time, right? And we get a 4 out and a remainder of 3. It's this remainder. I to the 127 is equal to I to the third power. What's I to the third power? I to the third power is -I. It's definitely worth it to memorize those first 4, that I to the first is equal to I. This one you'll use often, so no problem memorizing that one. I cubed is equal to -I, and I to the fourth is equal to 1. you actually never see an I to the fourth. If I did something like I to the 256, and we took 4 into 256, 4 goes into 25 6 times, goes into 16 4 times, and that has a remainder of 0. So this is equal not to I to the 64th, but I to the remainder, 0. Well, what's anything raised to the 0? 1. Where are we at? We're at this level right here, where we have all multiples of 4. So just to highlight that again, should be a repeat of what you had from your intermediate algebra instructor. If they didn't talk about it, go ahead and call them up and be like, what did you do? Okay, but I think you'll understand it. So identify each number as rational, irrational, pure imaginary, or non-real complex. Okay, so this first one is rational. If you remember, rational is all the fractions, right? And so how about this one? This is irrational, right? Pi. E is irrational, but it has an imaginary part, right? So E is irrational. So this is not pure imaginary. This is non-real complex because of that I. This is purely imaginary, has no real part. This is the non-real complex. I'll do NC. This is also the non-real complex. Okay, because it's not a real number, because it's got that. So the reason why they're saying non-real complex is because the complex number system contains the reals. Like negative 4/3 is in there, which is real. Pi, which is in there, is real. Square root of 24 is not a perfect square, so it's irrational. It's real and irrational. This is irrational. Square root of negative 25 is purely imaginary. Right? We know what that is. That's square root of 25, square root of negative 1. That's 5i. Right? That's what we've been looking at. And this is 6 minus 6i. And so that is non-real complex. So pretty fast to go through and do those. I don't think those are related to any homework questions, but these are, right? Solving equations. We're going right back to old stuff where we saw these things applied. And so it's really up to you how you do this. If you start to solve this, it's a great reminder of solving equations. We look for factors of 4 that add to be 3 and we'll never find any. So it doesn't factor. So we know that we're either going to complete the square or use the quadratic formula. Personally, I would use the quadratic formula for this one. So negative 3 plus or minus the square root of 3 squared minus 4ac all over 2a. Okay, and so what do we have? We have x equals negative 3 plus or minus the square root of 9 minus 16. And 9 minus 16 is a negative 7 all over 4. And that's why it's here, right? X is equal to negative 3 plus or minus square root of 7i. We want to get that I out of there. You leave the negative under there. I can't give you full credit. Now, our book may want us to split this into two answers. It's good every once in a while realize that there's individuals that never really understood the plus or minus at the level that they needed. There's two answers coming out. Okay, and I'm going to clean that last one up. Put a different square root over the top there. A plus root 7i and a minus root 7i. Easy as that. This next one is going to be the exact same level of difficulty. No problem. We just wanted you to know that there was a practical application that you were aware of here. Got brought up at the end of beginning algebra and in intermediate algebra. So here we have x squared minus 2x plus 2. Personally, I would totally complete the square with this one. Equals 0. So this is x. Whoops. Let me take it step by step and not freak you out. X squared minus 2x. So absolutely you could do the quadratic formula. It would work wonderfully. But it's way faster if you remember how to complete the square. Where if you say, oh, I need to add 1 to this side and 1 to this side. Oh, this is x minus 1, the quantity squared, and this is negative 1. Oh, take the square root of both sides, remembering my plus or minus. Oh, x minus 1 then is equal to plus or minus I, and x is equal to 1 plus or minus I. moving that 1 over. You'll get the same thing out of the quadratic formula, except you're going to have a lot of reduction that needs to take place. It's not an overwhelming amount. So certainly I can't argue that this is better, but you show something you should be aware of. They're going to have us just practice simplifying answers. Easy. Square root of 500 with the negative. Well, we know what the negative is going to do to us. The negative is just going to put an I on us. And then root 500, that's just 100 times 5, right? So the 10 can come out, the 5 stays in, and the I comes out. Doesn't matter how you write it to me. I've seen it in a lot of ways. 10I root 5, 10 root 5I. I tend to do the top one. How about 80? 80 is 16 times 5. So here's the negative from out there, right? That's just the negative going through. And there's a 4 that's going to come out, a 5 that's going to stay underneath, and an I that needs to be there. So negative 4 root 5I. Negative root 17 times negative root 17. Okay, so this is root 17I times root 17I. So root 17 times root 17 is 17. I times I is I squared. That's the way we should technically do it. And we get negative 17 out of that. Sorry. Coming through. So very, very much like what we did before. This is root 5I times root 15I, which is root 5 times 15I squared. So a 5 will come out, a 3 will have to stay underneath, and I squared is negative 1, so we're going to have negative 5 root 3. We get a nice, we took two imaginary numbers, multiplied them together, and got a real number. So those are two purely imaginary numbers that we multiplied together. So being careful here, let's reduce the root 12. Root 12 is 2 root 3, and then we have this I that's coming along. Root 6 can't reduce, so it looks like that. And root 8 looks like this. Oh, root 8, I apologize. I just saw what I wrote. This is 2 root 2. That's better. And so we can do some things. These 2's can go away. Everything's being multiplied. The 2 here can go into the 6 here and produce a 3 here, right? You can cancel inside with inside, and everything's being multiplied. So certainly we could kind of go through and multiply everything together, but this is your second, but actually third time simplifying roots. And so we can absolutely do this. Root 3 times root 3 is 3. I times I is I squared. And so we're getting a nice negative 3 out of that guy. And then here, this is 20 plus 2 root 2I, all divided by 2. Be careful with your canceling here. Because of this plus, if you're going to take a 2 out, you got to take it from all positions and get a 10 plus root 2I. So they're just reminding us about canceling and things like that. This next part's super easy. 4 plus 8, 12. Negative 1 plus 5I, 4I. Done. Right? And we get a plus 4I out of that. What's going to happen here? Well, we're just going to be careful with our signs. This is 3 root 7 minus 4 root 7 plus I minus 4I plus negative 2 root 7 plus 5I. Anything that has a root 7 can be combined. So here's 3, negative 1, negative 3 root 7s. Anything that has an I can be combined. Here's I minus 4I is now negative 3I plus 5I is now 2I. And we're just combining like terms like we were in pre-algebra. So these are nice pre-algebra problems. Don't get caught up with the I's there. They were just like variables in pre-algebra. Here's where it gets a little bit different than pre-algebra. We have to recognize that the I's aren't variables. So if we look at this one, this is very specific. We call this a conjugate pair. If we didn't recognize that and just write down what it should be, we could FOIL it out. Root 2 times root 2 is 2. Root 2 times 4i is plus 4 root 2i. Negative 4i times root 2 is negative 4 root 2i. And negative 4i plus 4i is negative 16i squared. And so look what happens. These middle terms cancel out, just like we knew they would from our experience in beginning algebra dealing with x minus 3 times x plus 3. Right? We love these conjugate pairs. In fact, have used them already in our class. This is 2 minus 16i squared. But remember, I squared isn't a variable. It's a number, and squared is negative 1. So now we got 2 plus 16, and we have the answer 18. So we took two complex numbers that had imaginary pieces to them, multiplied them together to get a real number, a nice number like 18. And so that's what's happening here, is we're just getting this Algebra 2 practice again. This has nothing to do with trig, just getting ourselves back in to this idea of imaginary numbers. So if we did one like number 78, the reason why they're doing this, if you're wondering why they're doing this, number one, because it has a trigonometric form, but number two, because this is their second opportunity to reinforce I numbers. The first time was in intermediate algebra class. So hopefully you remember how to square a polynomial. We would get 16 minus the 12 twice, so 12i is twice, I apologize, so I'm going to get 24 of them, and then plus a 9i squared, right? Just using our original math. So this is nothing different than what we did in beginning algebra. But that's different. I use the fact that I squared was negative 1. And that's why that sign changed from plus to minus. That's unique to our class. So what do we have to do next? Personally, I would combine the like terms that are there and get negative 5i. And maybe I'll start showing you what's changing by putting it in a different color. 16 minus 9 is 7. And this 24i is going along for the ride. Now the negative 5i is going through, so we get negative 35i minus, and then negative 5 times 24 works out to be 120, and we got an I squared. So we know about this I squared. This I squared is negative 1, so that negative 1 combined with that is going to make us have a, oh, I made a mistake. The mistake that I made was this was a plus 120 coming through. I don't know why I didn't see that before. The negative 5 times 7 is negative 35. Negative 5 times negative 24 is positive 120. So that negative 1 is going to hit the positive sign there. And they'll put it like this. They'll put the real part first, which is negative 120, and the imaginary part second. They'll always put it in the a plus bi format, and I would ask that you do the same. So if we look at this next one, if we grab these two and multiply them together, we know 3 times 3 is 9. Negative I times positive I is negative I squared. We don't need to do the middle one. And so let me just show you what we have here. Remember what I squared is. I squared is negative 1. So 9 minus a negative 1, well, we know what that is. From pre-algebra days, that's 10 times 2 minus 6i. And this is 20 minus 60i. And we're finished with that problem. I don't know if you remember how to get rid of an imaginary number on the bottom, but these problems are in succession, so it's very interesting that they totally know that you've seen this before, and so they're just having you work things. This problem's not finished. The weak student will think the 4's cancel and that the 3's cancel. And that's a very weak student. Like if you were tempted to cross out the 4's, you got some buffing up to do, right? Because you know division doesn't undo addition and subtraction. So, and the two things up on top and bottom, they're not the same. But the only reason we're not done is because we have this rule that you can't leave square roots in the bottom. You've been doing that throughout our class, getting rid of square roots on the bottom. There's no way we let you say that the tangent of 45 degrees is 1 over root 2. We had you rationalize it and call it root 2 over 2. And you did some of this rationalization with the chapter 5 work as well. Well, this is exactly what we were doing back in chapter 5. We picked the conjugate. 4 minus 3i needs to be multiplied to top and bottom. And so up top, we get 4 minus 3i times itself. Well, that's nice. Let's just do FOIL. 4 times 4, 16. 4 times negative 3, I, negative 12i. I'll space this one out. Negative 3i times 4, negative 12i. Negative 3 times negative 3, positive 9. I times I squared. We just did that one actually in problem number 78. I just combined those two to be 24 right away. 4 times 4, 16. 4 times negative 3i, waste of time. You know that you're not going to get a middle term, so don't do that. Positive 3i times negative 3i. A positive 3 times negative 3 is negative 9. I times I is I squared. Let's go make our I squareds negative ones, and let's see what we get. Let's talk ourselves through this. So what do we have? Right, we're good math students. We have 16 and a minus 9. 16 minus 9 is 7. Minus 12, minus 12, minus 24i. And that's exactly what we got back in 78 when you look in the parentheses. Right here. 16 minus 9 times negative 1. Well, that negative 1 is going to make this guy a plus, and we're going to get a 25. And we're finished. Maybe the back of the book would write it like this. In fact, they might, where they split the real and the imaginary part there. If they do, just try to do that in the homework and on the exam as well. If you have an I in the bottom, we need to get rid of it. Well, this is an easier one to get rid of. Everything's multiplied, so you can literally get by with multiplying top and bottom by I. Here we have 5i over 9. I times I is I squared. Don't leave it like that. 5i times negative 9, or over negative 9. And so probably should float that out to the front. But either way, I think I'm okay. I to the negative 14th power. Okay, don't stress about that. They're just using this as an opportunity to make sure you understand two things. One, what a negative exponent really does. Flips you. Two, the cycle of I. We know I repeats every 4 times, so let's figure out how many times 4 goes into 14. Goes in 3 times with 2 left over. So I to the 14th is equal to I to the second. Well, we know what I to the second is. We've been using it a bunch of times. It's negative 1. So this is 1 over negative 1, or negative 1. That easy. And then what about this? 1 over I to the negative 12? No problem. Pre-algebra tells us that that negative exponent down there will move to the top, right? Reinforced in algebra, used in algebra 2. And when we think of I to the 12s, think about how many times 4 goes into 12. Well, we don't care actually how many times, we care about the remainder. The remainder is 0. So this is the same as I to the 0, which is equal to 1. And we're finished. Okay. This says show that alpha is the square root of I. So keep in mind what they're asking. They're not asking you to find the square root of I. They want you to show that this is the square root of I. So, for example, if I wanted you to show that the square root of 49 is equal to 7, that 7 was the square root of 49, one thing you can do is just say, well, what does it mean to be the square root? It means if I take it times itself, I should get out 49, and I do, right? So they're claiming that this is the square root of I. So this number, this alpha, times itself better equal I. Otherwise, it's not the square root. The square root is something times itself that's equal to the value. And so let's just try it out. Root 2 over 2 plus root 2 over 2i times root 2 over 2 plus root 2 over 2i. So root 2 over 2 times root 2 over 2. This is going to be in almost every one, so just take a look at what it is up top. Root 2 times root 2 is 2. 2 times 2 is 4. So we get a nice 1/2. So root 2 over 2 times root 2 over 2, 1/2. Root 2 over 2 times root 2 over 2i plus 1/2i. Root 2 over 2i times root 2 over 2 is plus 1/2. Sorry, that came out really weird. Plus 1/2i. And then root 2 over 2i times root 2 over 2i is 1/2 positive I squared. So what do we have? We have 1/2 plus 2 i's make an I in the middle plus 1/2 I squared. Well, we know what I squared is. I squared is negative 1. That means this is negative 1/2, and it's going to cancel out with that. And so we do get our I. We get a nice negative 1/2 out of that last one. So hopefully that was able to be followed. Let me back up a little bit. Okay. So we have this 1/2 plus the I. Hopefully you see where the I came from. Half of I plus half of I is 1 full I. Minus 1/2, right? Because this is negative 1. The I squared. And 1/2 minus 1/2 is 0. So absolutely it is the square root of I. So a harder question is to kind of find that, but that's not what they asked us to do. That's the end of 8.1. So it's nothing new. It's no trigonometry whatsoever. We'll get to that in 8.2. This is just a reminder of Algebra 2, intermediate algebra.